Well, thank you for joining us. And today we are having the first of two sessions, which are the reports from the mentoring teams. There are a total of seven presentations that are scheduled. Two of them will happen today, and then five of them will happen next week. The two presentations that we're going to have today, the first one is from a team that I mentored. I'm almost positive I'm mispronouncing the team name, Kamsari-Gil, and their presentation topic is solving a puzzle. The puzzle is called Cugum. They're going to solve that puzzle on a quantum computer with a Hubo encoding and parity network synthesis. And then following that, we'll have a second presentation by Sang's team. The team name is Cutey, and they're doing a project on hybrid quantum machine learning. And I think we have about 20 minutes for the presentation, and then we can follow up with about 5 minutes or 10 minutes for questions and discussion. So if everybody's comfortable with that, we can start with our first team presentation. I guess I should ask first if there are any comments or questions anybody has. Okay. If not, then we'll turn it over to Chamsari Gill.
All right. Um, and everybody see the screen.
Yes.
All right. Thank you. Um, Hello, everyone. Thank you for your attendance early in the morning. Today, I'm going to talk about solving the Coogan puzzle on quantum computers with Hubo encoding and parity network synthesis. And just to briefly introduce our team, we go by the name of Chamsari-gil, and we are undergraduates from Korea University, majoring in electrical engineering and physics. So for the past 6 weeks, we have been trying to solve a problem that's called the Coogan puzzle. Now, there are some variations of this puzzle, but the one we aim to solve is shown in this picture. It's a 15 by 10 grid puzzle, and there are 40 pieces. So there are 8 different puzzle pieces, and each of them has 5 copies. And we want to formulate a cost function that takes x vector as input. Now, each element in the x vector is a Boolean variable that has values of 0 and 1. And we need to represent the displacements of the puzzle pieces with those variables and create a cost function that reads information from this x vector. Then we can convert the cost function into cost Hamiltonian, which then allows us to design a quantum circuit for QA/OA implementation. So the equation at the bottom is our general logic for the cost function. To briefly just explain the terms, S of x here, under the summation, is the function that takes the Boolean variables as input and outputs a set of tuples I, J, P, and R, which represents the positions and orientations of the puzzle pieces. And the function f here represents an indicator function that returns 0 or 1 depending on the cell occupancy. And with that being said, the first term you see here in the cost function, it penalizes the overlapping of the puzzle in R, where R is the reasonable puzzle grid. So if a cell is occupied by multiple pieces at the same time, it adds up to the cost function. And we implement a similar logic for the penalty area P. If a puzzle piece is present in the penalty area, the indicator function will turn on and increase the value of the cost function. And the lambda here is the hyperparameter that we can manipulate. And our goal is to minimize this cost function. Now, the problem is how do we want to construct this indicator function f? So our approach was using a displacement Boolean variable. So the big idea here is that there are displacement Boolean variables, h and b, that can represent the horizontal and vertical movements of pieces. Oh, and rotations as well as shown in the code, but we'll talk about this later. We used a Python module called SymPy to return the symbolic expression of the indicator functions. So let me give you an example of how this will work. Say there is a 1x1 puzzle piece in the 2x4 grid shown below. If the piece occupies this cell at the top left, the input x will have a h0, h1, and v0 variables equal to 0. So if we write our indicator function like this, only the top left cell will return 1. And let's move this piece 1 block to the right. And in this case, we just need to write h0 instead of 1 minus h0 because the value of h0 from the input will be 1. And with this logic, we can represent the displacement of the piece for the entire grid. And so now we need to account for the piece and rotation information. And to do so, we create a shape function that assigns relative coordinates to the pieces, depending on the piece and rotation information. And the reference point of the relative coordinates is set as the leftmost, topmost position of the piece. And this function will be used when implementing the indicator function. And the reason why I use relative coordinates is to give more flexibility to the code. So yeah, if we have this 15 by 10 grid with the origin at the top left, the reference point would be at the red dot here. And the relative coordinates for this L-shaped piece are as follows. And now we can implement the indicator function. So first, this indicator function sets the number of valid rotations for each piece using the num_r list. And for each possible rotation of P, it calculates how many valid positions of block P can cover the grid cell I, comma j, and sums the symbolic delta function terms for each possible placement. And it returns a SymPy expression representing the total coverage of I, comma j by block P across all allowed rotations within the grid boundaries. And next, the function modifies this symbolic term based on the rotation. Since rotations are encoded as binary variables, the function uses binary representation of the current rotation to attach symbolic weights. So for example, if there are four possible rotations, so the binary string would have a length of 2, the function multiplies expressions like r0 times 1 minus r1 to ensure that it only contributes to the indicator function when the rotation variables match that specific rotation. And this selective filtering ensures that the term contributes only if both the position and rotation of the piece match the setting that causes it to cover I, comma j. And now for the grid allocation, we have to set not only the puzzle grid, but also the penalty grid. And since we set our reference point of the pieces as the leftmost, topmost location, this constrains the penalty area to take this form, the picture you see on the right. And the size of the penalty area was determined with the consideration of the size of the pieces. And we coded our R and P grid because we need to sum the values of the indicator functions in both areas for the cost function. And then we also need to decode the input x vector so we can substitute the necessary information into the indicator function to evaluate our cost function. So the input takes form of Boolean variables that contain H, V, and R information about the pieces. And the information is ordered in increasing p-value. So like the first 8 bits have the information about the 2x2 piece where p equals 1 with no rotation. And this repeats for the other 4 copies of that puzzle piece. And then the next 9 bits have the information about the 1x2 piece where p equals 2 with 1 rotation, and so on. And this sequence gives total bit string length of 385. And as for the coding, the splitter function splits the binary string X into substrings corresponding to each piece's full configuration, so position and rotation, based on this position counts dictionary. Then the decoder function interprets each of the substrings from the splitter into a dictionary with displacement labels on it for each bit. And it always extracts the horizontal and vertical position bits, so 8 bits total. And then depending on how many more bits there are in the substring, it interprets them as 1 bit, 2 bit, and 3 bit rotation. So we use our decoder function to decode our input bit string and then generate our puzzle grid and the penalty grid. The block coverage cost function returns a symbolic expression for the overlapping term. Each piece is assigned a shape by this arithmetic, since there are 5 pieces per shape. And we substitute our decoded values into the indicator function. And if a cell is covered only once, we give no penalty from our logic of indicator function. And then the grayed out cost was implemented in a very similar manner. And we multiply the hyperparameter lambda to this grayed out cost function and add this block coverage cost function to obtain our full cost function. So this was the coding aspect of our project. And now we want to minimize the number of C0 gates used to implement this unitary operation for the QAOA, because 2-qubit gates are more prone to errors and it takes longer to execute than single-qubit gates, which impacts overall efficiency and accuracy of quantum computations. So this first algorithm is designed to construct a parity network, which is a sequence of C0 gates that transforms the initial state of qubits into a state where all required parity terms from the Hamiltonian appear in the computational basis at some point. And the algorithm operates in a greedy manner, meaning it makes locally optimal choices at each step to minimize the number of C0 gates required. This process begins with a set of parities S, where each element represents a term in the Hamiltonian. The algorithm iteratively reduces the parities in S to unit Hamming weight. And at each step, it selects the parity with the smallest Hamming weight, applies a C0 gate to simplify it, and updates the remaining parities to reflect the new basis. And this continues until all parities in S have been incorporated into the basis, meaning that they appear as individual qubit states at some point in the circuit. And the reason we do this is because first, it reduces the number of C0 gates while implementing the multi-qubit RZ gates. So instead of like the implementing RZZ and RZZZ gates in a traditional way, using this parity network, we can do the same thing and then also minimize the number of C0 gates used. And then we have to invert the parity network because we don't want to permanently change the basis or qubits. And this step is crucial because QAOA requires the mixer layer to act on the original qubit states, not the transformed ones by the algorithm 1. And that's what algorithm 2 does. Starting from the final state matrix produced by algorithm 1, this algorithm iteratively selects pairs of rows where CNOT operation will maximally reduce the Hamming weight by always choosing the row with fewer ones as the control to minimize gate identity, gate count, sorry. Each CNOT application performs a row operation that simplifies the matrix towards the identity, with the process repeating until all qubits return to their initial states. And this approach efficiently inverts the parity network by leveraging the structure imposed by algorithm 1, ensuring the complete circuit implementation, and it can perform the desired unitary operation with minimum use of CNOT gates. And we apply these algorithms to our Coogan puzzle problem. But when we were converting the cost function to cost Hamiltonian, we were not able to compute the Hamiltonian for the 15 by 10 grid because the size of the problem was too big. So we reduced the problem size to 4 by 4 grid. Then we computed the cost Hamiltonian for the 4 by 4 grid. And for lambda, we substituted in a value of 100 to strongly constrain pieces going out into the penalty area. And the histogram on the left, it analyzes the frequency of the order of Z terms. And from this histogram, we can naively estimate the number of CNOT gates required to implement the cost Hamiltonian on a QAOA circuit, because for our ZZ gate, we need 2 CNOT gates. And for our ZZZ gate, we need 4 CNOT gates. And generalizing this to any order of Z gives the formula of order of Z term minus 1 times 2. So multiplying the number of terms in that Z order and summing over all possible orders of Z terms resulted in a value around 166K, which hints that the upper bound for the number of CNOT gates to implement the cost Hamiltonian is around 166K. Also note that the maximum order of Z is greater than 2, so this whole Coogan puzzle problem is a Hubbell problem rather than a Hubbell problem. This is after applying the greedy algorithm with the same Hamiltonian. And the number of CNOT gates, as you can see here, is around 21K, which I find very remarkable. And to conclude, we have formulated a cost function for the Coogan puzzle for the 15 by 10 grid. And we formulated it such a way that it can be easily generalized to a Coogan puzzle with arbitrary grid size with more or different pieces. So when we realized that the sheer dimension of the 15 by 10 problem was too big, we narrowed the problem down to a 4 by 4 grid and converted the cost function to cost Hamiltonian by substituting x equals 1 minus z over 2. Then we compared the number of CNOT gates before and after the application of greedy algorithms, which resulted in around 87.6% CNOT gate reduction. And what we have done for this Coogan puzzle can be potentially extended to a bin packing problem, which is a combinatorial optimization problem where a set of items, each with a specific size, must be packed into a minimum number of fixed capacity bins. And the objective here is to allocate all items without exceeding the capacity of any bin. And I found this very similar in nature to the puzzle problem that we've analyzed. And yeah, this is it. Thank you for listening. And any questions would be appreciated. Thank you.
I have a question and also a comment. Can you go back a few slides to the 2 slides that, yes. So this slide here uh, you call this greedy algorithm, but actually the greedy algorithm is really on the next slide. This is really, I would say, the naive algorithm, right?
Oh,
Because there's
this,
no that greedy heuristic is not applied with this accounting for the C naught gates here.
yes. So this histogram is made from the Hamiltonian before the application of greedy algorithms, and this is after.
Okay.
So what I've done,
And then the question I had was for the 4 by 4 problem, how many qubits did you end up needing?
I think it was 23.
Okay, thank you.
I also have a couple of questions. First of all, thank you for the very nice presentation.
Thank you.
For um, the grid, say you mentioned 4 by 4 grid, and I think Denny already asked, like how does the number of qubits scale with the grid size? You mentioned a 10 by 15, for instance. How many qubits would you need to encode the problem?
For 15 by 10 grid, I think we needed like 385 qubits.
Okay, it's
But
because you have
we
the grid and the penalty area. Each location is basically a qubit. Is that correct?
yes.
Great. And then my other question is for the 4 by 4 case, you mentioned that after optimization, it's roughly 20,000 C naught gates, correct?
Yes.
So that
Yes.
sounds, of course, too much for NIST, but of course, you can simulate this on a pure state simulator, right? Just a
Tech-
noiseless simulator, you could totally simulate this. Have you done this? I'd be very
yes.
curious to see if you get the actual solutions.
We have not, but like you've mentioned, I think in a noise-free simulator, this can be simulated, and um, yeah, we'll try this.
I think it
We
would be
haven't done it.
extremely fun to see what solutions this algorithm comes up with.
Mhm.
It's a great algorithm and great use
Yeah,
case. I really love it.
thank you.
I've seen things like that before for Sudoku.
Uh-huh.
Is Sudoku easier than this puzzle? I assume yes, but just wanted to check.
But doesn't Sudoku require more, like, doesn't it have like larger, grid compared to
But
like 4 by 4?
9 by 9, but not every cell will be occupied.
That's true.
And the constraints,
But
I
I
think,
haven't been,
are very nice there.
yeah, thank you for your comment.
Thank you.
Are there any other questions? If not, let us thank the team. That was a very nice presentation.
Thank you very much.
Um, Now, our next presentation will be Sang's team. Sang, would you like to introduce your team?
Oh, yes. The team that I mentored is the name of the team is Cutey, and they tackle the problem classical quantum hybrid machine learning, and they are tackling image problem using vision transformer and using quantum method. So, yeah, please present the results, your effort. Yeah, thank you.
Okay, thank you for introducing us to Sang Kim. Okay, let's start our presentation. Okay. Can you see this? Okay. Hello, this is Jisoo Han from Team 10. Today, our team will be presenting on the topic of quantum hybrid machine learning. Through this topic, our goal was to achieve quantum advantage. Here is the outline of our presentation. First, background, then dataset, and finally, our proposed model. The ultimate goal of quantum machine learning is to leverage quantum properties like superposition and entanglement to accelerate data processing or improve learning efficiency. In particular, PML aims to provide quantum advantage in solving high-dimensional problems that are difficult for classical machine learning. Quantum model can represent complex patterns in high-dimensional spaces with relatively few parameters. For certain tasks like pattern classification or optimization, they have the potential to be faster or more accurate than classical models. In line with this, both theoretical and experimental studies have shown that quantum soft vector machines, such as QSVMs, can outperform classical SVMs in classification tasks. In QML, a common approach involves inserting trainable parameters into gate with a parametric quantum circuit, measuring the output to compute the rules, and updating the parameters using a classical optimizer. Another approach is designing quantum neural network based on quantum gates, where quantum states are used as inputs for learning. QML has a wide range of potential applications, including classification and regression tasks like QSVM. Complex optimization problems in logistic finance and resource allocation and quantum chemistry, such as chemistry and material simulation, such as predicting molecular energy levels or drug discovery. Now, let me introduce the data set we used. RetinaMNIST is one of the many data sets from MedMNIST, a collection of medical data sets designed for lightweight and accessible reach. It was created to support the classification and diagnosis of various ophthalmic diseases such as diabetic retinopathy. Since analyzing retinal disease data holds significant clinical value, many researchers have used this dataset to develop and evaluate their model. Retina images typically have high resolution and structural complexity, which can be computationally expensive using classical methods. RetinaMNIST, while containing 5 classes, has a relatively small number of samples. These characteristics make it a suitable challenge for testing the efficiency improvement that quantum machine learning may provide. Based on these points, our team decided to use RetinaMNIST as the primary data set for applying quantum machine learning. Okay. In short, our strategy is to extract. Let's go next page. We choose Med Visual Transformer version 2 in our baseline model. Med Visual Transformers version 2 is a hybrid backbone designed for medical image analysis, combining CNNs for local feature extraction and transformer for global context. The architecture is composed of 4 stages. Stage 1 uses dilated neighborhood attention for capturing local patterns. From stage 2 onward, both local CNN based on blocks and global transformer based blocks are applied in sequence. As we move through the stage, global feature perceptions becomes more dominant, ending with the classifier. The attention modules shown in the both right use multi-head self-attention with token enhancement via average play. Overall, MedVisual 2 version 2 effectively integrate local and global representation, providing a strong feature backbone before applying quantum enhanced classification. The MedVisual transformation baseline provides multiple modal variants: T for tiny, S for small, B for basic, and L for large. Each version differs in terms of parameter count, computational cost, and representation power. For our project, we selected the MedVisual Transformer Small version, as it offered a good balance between efficiency and performance. Additionally, as shown in the baseline result, the retinal amnest dataset tends to show lower accuracy compared to other datasets. This observation also motivated us to choose retinal amnest as our primary benchmark for further investigation. We utilized MedVisual Transformation version 2 as a backbone to extract feature maps from input images, which were the passed into quantum circuit. Now we would like to walk you through the structure of each model we designed and compare their performance metrics. The first model we proposed is the hybrid QuestVM. It incorporates a hybrid architecture using a quantum corner trick with a classical SVM. In this model, we use the classical Vision Transformer version 2 backbone for feature extraction, and replaced only the classification part with the quantum circuit. The 512-dimensional feature map extracted from baseline was reduced to dimensional using PCA, and those 12 features were angle embedded into a quantum circuit to represent them as quantum states. Then, by applying the quantum corner trick, the data is mapped into a high-dimensional Hilbert space, enabling better separation of class during classification. Next, let me explain how we embed the feature vector from our medical transformer into quantum information. First, we use our gate to encode each feature value as a rotation along the x-axis. In our implementation, we use the Kremlin angle embedding from penny lane for this purpose. To introduce entanglement between neighboring qubits, we apply the Ising-Dizzy gate also from penny lane. This gate uses the Pauli-G matrix and allows control over the strength of entanglement via parameter theta. Unlike the CNOT gate, the Ising-Dizzy gate let us tune the level of entanglement, which can be optimized during training. However, in our case, we fix theta to pi due to some training issues and proceed connected with that value. After the entanglement step, we applied another RX gate for post-processing. This additional rotation enhances the expressivity of the circuit and helps capture more complex decision boundaries. For measurement, we use Kreml probes, which gives the full probability distribution over our basis state. This entire circuit is applied to 12 qubits, and to reduce the gate count, we only introduced entanglement based on odd-even qubit pair. Through this quantum embedding process, we efficiently represent high-dimensional retinal features with a compact set of quantum parameters. The entanglement via Ising-Dizzy helps capture complex interactions between features, ultimately improving classification performance compared to classical model. To extract more meaningful feature maps, we applied contrastive laws to the 512 dimensional features produced by base model. The goal was to pull together samples from the same classes while pushing apart those from different classes in the feature space. By doing so, we aim to enhance the class separability of feature vectors so that the quantum model receives input data that is already well clustered and easier to classify. This helps the quantum classifier focus more on learning decision boundaries rather than struggling with raw entangled feature representation. In this graph, we can observe the contrastive laws decrease steadily throughout training. This indicates that the model is learning to group similar classes closer and separate different classes more effectively in the feature space, which confirms that the contrastive learning process is working as intended. However, despite our expectations, we did not observe a significant improvement in classification performance. Although contrastive learning helps structure the feature space, the accuracy remained largely unchanged. There could be multiple hypotheses explaining why this happened, and I will discuss the possible reasons later in the presentations. This is a 3D visualization based on the features extracted from our first proposed model. As mentioned earlier, we can clearly see that the feature vectors are not well separated by classes, indicating poor classification boundaries. This supports our earlier observation that the model struggled to distinguish between classes effectively. Now let me present our second model. In this approach, we aim to enable learning by incorporating a high quantum neural network. As mentioned earlier, we kept the same picture extraction process and quantum circuit design. However, in this model, we attempt to perform the final classification using fully connected layer. In this model, the loss design follows a similar approach to the one used in our previous proposal. For the mad visual transformation version to backbone, we applied contrastive laws to guide the feature extraction. On the other hand, for the quantum circuit branch, we used cross-entropy laws. This setup was intended to train the feature extraction and classification networks separately while still allowing them to be optimized in coordinated manner. However, as we can see from the loss graph, While the contrastive loss decreases steadily, the classification loss does not showing significant improvement. This suggests that the quantum circuit is not performing effect classification, leading to insufficient learning on the side. We believe that a main reason for this is the lack of entanglement between qubits. Since the original circuit design focused on minimizing the number of quantum gates, the expressivity of the circuit maybe have been limited, which ultimately affected the classification performance. Due to this insufficient learning, we observed the overall performance of the QNN was significantly lower compared to the baseline model. As a result of insufficient training, the 3D visualization also showed that the features were not well separated, indicating poor classification performance. Next, I would like to present our second model, last model. We extracted features using pre-trained medium visual transformation model and embedded them into the quantum circuit using amplitude embedding. The architecture includes a quantum convolutional layer followed by a quantum pooling layer to reduce the dimensionality. And finally, classification is performed through a quantum-fully connected layer. For training the DQCNN, we used cross-entropy laws to optimize the network. In the quantum convolutional layer, entanglement is applied between qubits to enable a more expressive feature transformer. The quantum pooling layer then measures selected qubits, effectively reducing the number of qubits and compressing the information. Through this process, the original 512-dimensional feature is reduced, and the model ultimately classifies the input into one of 5 classes. This model showed an accuracy of approximately 46%. However, due to the long training time, we were not able to complete the full training. Now, I'd like to briefly discuss the limitation faced and directions for future work. First, regarding PCA, since it is not a runnable layer, it may not have delivered sufficient information to the quantum network. This likely limited the quality of features past the quantum layers. Second, with contrastive loss, due to its nature, it requires a large amount of training and fine-tuning. This added a significant training burden, especially when used alongside quantum components. As for future work, we plan to explore alternative backbone models for feature extraction instead of relying solely on individual transformation version 2. We also aim to experiment with different dimensionality reduction methods other than PCA ideally, ones that are learnable and adaptable. Finally, as more qubits become available and more expressive, quantum circuit can be designed. We expect this will help the models capture richer information and ultimately improve performance. That's the end of my presentation. Thank you so much for listening.
Thank you.
Thank you.
Maybe I can I ask questions, Danny? Okay. Thanks for the presentation. And so you compare the results of the paper with your model, and your model is using these quantum layers. Have you actually tested with classical counterparts like a neural network or SVC, or do you have the results that actually?
Yeah, we try to classical SVC, not using quantum information. Yes, but we watched the performance of classical SVC about 70%.
You mean AUC, and what about ACC? Like
ACC, in my memory, maybe about 49 or 50%.
oh,
AUC is
0.5,
about, yeah,
0.49 or 0.5. Okay.
yeah, 0.5. Yeah.
Martin has a question.
Yeah, thank you very much for the nice presentation, first of all.
Thank you.
Question is, how do you represent the different color channels of the image, and how big are the channels, and how do you load those into the quantum model? Does that make sense? Does the question make sense? The red
Channel,
images you showed looked like RGB images. Do you treat all
yeah.
differently?
Yeah. We use the RGB channel, so we have a three channel, and as I presented, all feature extracted using classical baseline. So we get the 24 batches and 512 features after the extracting features. So our team did not think about the channels, because we trusted baseline models extracted the feature map very well.
And if I give some more context,
Yeah.
so they use a vision transformer. So all this RGB information is taken care of by this pre-trained vision transformer. And the vision transformer outputs 512 dimensional embedding vectors. And they use a PCA to do the dimension reduction from 512 down to 12. Then they use angle encoding to load this information to the following quantum layer.
Great. That was my next question, how you encode. So you use basically 9 qubits to represent the image then from 512?
9 qubits. Maybe you did this one.
Yeah.
Yeah. This is because the two this is because I can't remember in English.
Can I assist the team, Martin, in Korean?
Yeah.
Yes.
예,
Okay. 일단 지금 마틴이 질문하신 거는 지금 이 12디멘셔널 벡터를 몇 개의
예.
큐빅을 했냐는 질문이거든요. 그러니까 12입니다. 12, 예.
12요. 9 9큐빗이 아니라 12를 몇 개의 디멘셔널로 했는지.
그러니까 PCA에서 나온 값을 몇
네.
개의 큐빗에 사용했는지에 대한 질문입니다.
We use 12 qubits because we have 12 features after PCA. So we really want to one feature map to one qubit to embedding. So we use the 12 qubit.
Okay. And the final output, if I remember correctly, there were 5 classes. Is that correct? So you have 3 cubes at the end that you measure, or how do you do it? How do you produce the final answer?
Actually, we used some tricks. We have 8 probabilities. So we reduced the 8 to 5. So actually, so we have 8 probabilities and to reduce the 5 classes.
Yeah.
Yeah.
Do you pick the most likely ones? Or how do you go from those 8 to 5?
Yeah, let me assist this screen. Martin, sorry. So, 그래서 지금 그 측정한 거에서 어떻게 5개의 클래스의 프로버비티를 어떻게 5개의 그 5클래스니까 5개의 클래스의 프로버비티를 하냐는 질문입니다.
Actually, in QNN, we use the fully connected layer in the last layer for our probability from measurement quantum circuit. So we use the fully connected layer in last layer in
Oh, I
QNN.
see.
Yeah.
I see. It's the final fully connected last layer.
Yeah. So, and we compared this label and original label with cross entropy, and we train the quantum circuit and the contrastive loss train the baseline model. Yeah. So actually, it is not end-to-end train. It is separate the train.
Yeah, I understand.
Yeah.
Okay, thank you very much.
Thank you.
Are there any more questions? Well, I'd like to thank both the teams. I think you've done great work. It was very interesting to hear your presentations, and we will look forward to hearing some more next week. Thank you very much. Bye,
Thank
everybody.
you.